Okay, so the next theorem we want to talk about is the divergence theorem, which is a great theorem in order to find a surface integral or a flux. The only thing is that something very specific has to happen in order to use this integral. So it's sort of a shortcut for a surface integral. But you have to have a three-dimensional solid region that it is bounded completely. So it has to be completely surrounded by surfaces with positive orientation, and remember this means outward orientation. And then we could say that a surface integral is equal to a triple integral of the divergence of f. So we find the divergence, we set up a triple integral over that three-dimensional solid. Okay, so let's do an example, and I'm going to do this on a separate piece. So let's find the flux of the vector field, what should we do, x squared, xy, and z over the surfaces. Over the surfaces, z equals 4 minus x squared minus y squared and the xy plane. Okay, so now normally, if we did this with a regular surface integral for the flux, this is over surfaces, two different surfaces. And that means that we would have to have two different surface integrals to calculate in order to find this. But the divergence theorem is going to make this pretty nice, as long as those surfaces completely surround a three-dimensional solid. I'm going to graph them. The z equals 4 minus x squared minus y squared. That's a paraboloid. Top of it is at 4. Goes downwards. And this stops at the xy plane. All right, so it completely surrounds because we have the surface of the paraboloid, and then we've got this little circle down below too. That's the xy plane. So we have this three-dimensional solid completely covered. So in order to find the surface integral, we're going to do that with a triple integral of the divergence of f. So let's find the divergence of that vector function. And remember that divergence is a function when we take a partial of the x component of f with respect to x, and that derivative is 2x. Add to it a partial of the y component with respect to y, and that derivative with respect to y is x. And a partial of the z component with respect to z, and that is just 1. So we get 3x plus 1. So now to set up our triple integrals, we are going to have a triple integral of 3x plus 1. Now, our most complicated function, so the function that would be on the inside integral, I say our most complicated function is z. So I'm going to do dz first. The upper bound of z is the paraboloid, so that goes on the top. 4 minus x squared minus y squared. And the lower bound is 0. Now the other two, the outer two, we need to look at the xy plane, and if we look at the xy plane, we get a circle, and now we're in polar coordinates. Just need to figure out that radius. So that radius is going to come from when z equals 0, and z is also equal to 4 minus x squared minus y squared, and we get the circle, x squared plus y squared equals 4, so our radius is 2. All right, So now I'm going to redraw this integral because I now need to convert everything into polar coordinates. So converting that function, well, x is r cosine theta. All of that needs to be multiplied by r. Z is still going to stay as z, and I'll have dr d theta. Now for the z bounds, those have to go to polar coordinates, 0, 0. And 4 minus x squared minus y squared would be 4 minus r squared. And radius, that goes from 0 to 2. We just found that. Theta, it's a full circle, 0 to 2 pi. Okay, so integrating with respect to z first. So I'm going to multiply through by r while I do this as well. So we're going to have 3r squared cosine of theta plus r, all of that, times z, and we need to evaluate that from 0 to 4 minus r squared. We still have to integrate from 0 to 2 pi, we still have to integrate from 0 to 2, dr d theta. So now plug in 4 minus r squared for z. So I'm going to have to FOIL this whole term, and for space I'm going to do that right now. So I'm going to have 4 times 3r cosine theta. That's going to be 12r squared cosine theta plus 4r, so that's multiplying 4 by each one of those terms when I plug it in for z. Then I'm going to multiply negative r squared by both of these terms. So negative r squared is going to give me a negative 3r to the 4th cosine theta minus r cubed. Dr d theta. Need to integrate from 0 to 2, integrate from 0 to 2 pi. Okay, so now integrating with respect to r. I'm going to have, let's see, we'll have r cubed divided by 3, and 12 divided by 3 is 4 cosine theta. R squared divided by 2, so 2r squared, minus 3/5 r to the 5th cosine theta minus r to the 4th over 4. To evaluate that from 0 to 2, we still have to integrate over theta. Boy, I'm going to run out of room. Okay, so when we plug in r, so 2 cubed would be 8, and 8 times 4 gives us 32 cosine theta. 2 squared is 4. 4 times 2 gives us 8. Minus, let's see, 5. 2 to the 5th is going to give us 32 times 3. I think that's 96 fifths cosine theta. And 2 to the 4th is 16 divided by 4, so that would be a minus 4. I still have to integrate from 0 to 2 pi. Okay, so now integrating with respect to theta. So I will get 32 sine of theta. I'm going to combine this 8 and this 4 into a 4, so that would be plus 4 theta minus 96 fifths sine of theta, and evaluate from 0 to 2 pi. And I am running out of room, and luckily enough, I've got 2 sine functions in here. They're both going to go to 0 because the sine of 0 is 0 and the sine of 2 pi is 0. And all that I'm left with is 4 times 2 pi, which gives me 8 pi. So this integral took a little bit of time here, but notice that setup. Yes, it took a little bit of thought, but that That to me was way easier than calculating two different surface integrals over two different surfaces. So that's what the divergence theorem does for us. It gives us a nice way to evaluate a surface integral, but once again, those surfaces have to completely surround the 3D shape in order to do that. If one of the surfaces is missing, we can no longer use the divergence theorem.